In this video, I'm going to teach some of the features of the NMR processing software. To follow along with your own version of MNova, the file that I'm going to work with is found on the N drive, Chem 240, Lab, Spectral Problems, capital E series, EA series, EAB, EABH1, and FID. I'm also going to open at the same time the C13 NMR file for that compound. So one nice thing that you see immediately with MNova is you can have multiple files open at the same time. This is the proton for EAB. This is the carbon for EAB. When you work up a file, one of the things that you need to do first is to reference the file. So one particularly useful hotkey in MNova is Z for zoom. You can zoom horizontally, you can zoom vertically, or you can just zoom as a box. If you don't like keyboard shortcuts, these are the options up here for zooming. And if we zoom in on this region of the spectrum between 4 and 0, what you see is we've got a peak at 4-ish, a peak at 2, and a peak at 1.2. We also have a peak at 0. The peak at 0 is invariably a reference peak known as tetramethylsilane, TMS, and if you click on that, you can now shift the spectrum ever so slightly, and that sets this at reference. The TMS peak should be at 0.00, so I have now set that to be true. If you would like to go back to the original level of zoom, you just hit this button here for full spectrum. And now I want you to draw your attention to this very small peak down near 7 and a little. This peak here, and you can increase the intensity of the spectrum by rolling the mouse wheel or by using these buttons here, is invariably chloroform. And so you can also alternatively reference the spectrum by selecting this peak and setting that to be 7.26 if the spectrum was taken in CDCl3. Notice now that this spectrum is very much off scale in terms of intensity, so I'm going to decrease the intensity or scroll with the mouse in order to get it back down. The next order of business when we are analyzing a spectrum is to do some integration to figure out how many hydrogens each one of these peaks is worth. In order to do that, what we need to do is to zoom in on the peaks of interest again. So if I zoom in between 4 and 1, as those are the only 3 peaks of interest, then what you see is we have a quartet, a singlet, and a triplet moving across. If you simply click on integration, what happens is it artificially integrates for you. That may or may not be the way you want to do it. I strongly recommend integrating manually. So you'll notice that what we have here is a drop-down menu. Delete all gets rid of all of those integrals. Instead, what I prefer to do is to integrate manually, and then you just drag from left to right across the baseline of each of these peaks and define the integral regions. Now, for some of you, it may be very difficult to read what these numbers say. So if you want to change that, what you can do is simply right-click in the middle of the spectrum somewhere, come down to Properties, and then you can change all of the numbers. So for the integrals, if you want to be able to see those better, I recommend changing the font and simply making that font much larger. If you simply hit Apply, notice how you can now read those numbers. By the same token, you can change all of the numbers. If you want to change the scales, we can adjust the font. And if you want to change the peaks, which you're going to want to do, first you must define peaks, and then you can change the font there. And while we're doing these adjustments, I recommend verifying that there are 3 decimal places on the peaks. Okay, let's close this back out. Now look at the integrals. What do you see? An integral worth 1, one worth 1.6 or 1.5, depending on how you like to round, 1.5 there. And so what we see is this is a meaningful number in terms of NMR. You can have one hydrogen atom. You can't, however, have 1.5 hydrogen atoms in a spectrum. And so what we should probably do is rescale these. The only reason why this is scaled to be 1 is because we integrated it first. Allow me to demonstrate by deleting all the integrals and now integrating this one first. That is defined to be 1. That is defined to be 1. And this is now 2/3, give or take. So, we must decide what each of these peaks is really worth in some sense. I think you'll find that when you are studying NMRs, if you have a relatively tall peak that's a singlet, one of the things that you should try is to set that integral to be worth 3. In order to change what an integral is worth, you must right-click on the spectrum when you have this red bar illuminated, and that should give you the option of editing the integral. Then you can come down here to normalized and set that to be worth 3. So this is now worth 3 hydrogens. This peak here is worth 3 hydrogens, and this peak here is worth 2 hydrogens. This should make more sense to you than having it be worth 1 and 1.5. You can have 2 hydrogens, you can have 3 hydrogens. Now we can start trying to figure out what might give rise to a signal of 3 with no neighbors. I want to highlight something else about the integral situation as well. We can again delete all the integrals and go back to the original system that I had here, where we had 1 for the first integral, 1.5 for the second integral, and 1.5. We can clearly see that 1, 1.5, and 1.5 does not necessarily work. But we don't necessarily want to choose what this one is worth, so we can simply try other integers. For example, if we try 2, then what you see is this peak is worth 2, which makes sense. This peak is worth 3, which could make some sense, as well as this one. And so there's nothing necessarily wrong about these integrals. But if you would like to try a different integer, we could set that to be worth 3, for example. Now what we have is a peak worth 3, a peak worth 4.7, and a peak worth 4.6. And so I think you'll agree that this doesn't feel quite as good as the right integration, and that what we really should be using is an integration of 2 here, because 2, 3, and 3 works better than 1, 1.5, and 1.5, or 3, 4 and a little, and 4 and a little. Once you have set the integrals to be something meaningful, then we have more or less concluded the integration portion of the workup. Moving on to the next step, what we should do is peak picking. Again, you have the option of simply clicking on the peak setup, this little pincer looking thing, but you'll notice that what happens when we do that is you get a bunch of different signals being highlighted as peaks, and I don't think that these are meaningful little peaks that we need to worry about relative to the intensities of everything else. So once again, I think that the program doesn't do a nice job of selecting the right peaks. So instead, what I like to do is to insert the peaks manually. So delete all, and then if you come over here to manual, what you now should do is to define the peak region. So the little horizontal bar is what allows you to decide what counts as a real peak and what doesn't. And you can simply go across and do so for all peaks that you consider to be real. Notice that I'm ignoring these tiny little peaks here that are just barely visible because I don't think that they are meaningful. Now it's time for some analysis. We're going to try to identify what the molecule is. Notice that when I first encountered the spectrum, I described it as a quartet, a singlet, and a triplet, because at the level of zoom that we've been looking at, that appears to be true. Having said that, it is sometimes useful to go ahead and zoom in a little bit more closely. So let's examine this peak more closely. And while it has a funky shape to it, I think we'll all agree that this is a quartet. We have a 1 to 3 to 3 to 1 height ratio, which suggests that this is a nice regular quartet. If you want to zoom back out, you could always zoom all the way back out, or you could just hit Control Z if you're a PC user, or undo essentially, and come back to where we just were. If we now zoom in on the supposed singlet, what you see here is that indeed it looks like a singlet, albeit a singlet with a little bit of a funny shape here. Clearly the shimming on this particular spectrum was not as good as it could have been. But this is the spectrum that we're analyzing. Let's zoom back out again. And once again I will zoom back in on the middle region. And now what I'll do is zoom in on this peak, which I originally called a triplet. Notice that the computer appears to be describing this as a 4-line pattern and not a 3-line pattern. What the computer is identifying are the 3 lines that we see, as well as this tiny little shoulder. I think you'll agree with me, though, that this peak is better described as a triplet with a 1 to 2 to 1 intensity as opposed to something else. So if this is a triplet, then this spectrum begins to make some sense. However, for the purposes of recording the peak numbers, you would want to keep in mind that this number right here is clearly bogus, and what we're looking at is 1.195 as this major peak. Let me zoom back out once more, and once again I want to zoom in on the TMS peak. Notice that something strange is going on in this spectrum. When we originally referenced to the TMS at 0, that set the chloroform to be in the wrong place. If you have TMS present, you should set that peak to be the one that is referenced. If you do not have TMS, then you can use chloroform as the reference. Let me zoom back out once more and zoom back in. So what we have now is this spectrum in the proton, and we have now worked this up completely. We have referenced the spectrum to 0 with TMS. We have integrated the peaks down here. We have not selected the appropriate integral, apparently, so I will edit integral and set this to be 2, because 2 to 3 to 3 is a better set of integrals than 1 to 1.5 to 1.5 in terms of interpretation. And we have picked the peaks. We've identified that this is really a quartet, this is really a singlet, and this is really a triplet. That is all that we can do as far as the Proton NMR working it up before we start drawing things. So, moving on to carbon NMR, in order to work up the spectrum, we must follow a similar sequence of steps. The first level of analysis when you are looking at a carbon is how many peaks are present. In carbon NMRs, we don't care about integrals, so all we need to do is figure out how many peaks are present, reference the spectrum appropriately, and also to identify where the peaks are. One particular peak I want to highlight is this one here. If you have a sequence of 3 peaks that look identical heights like this, what that means is that this is chloroform, CDCl3. Deuterochloroform has this pattern always, and if you see a pattern like this in a carbon NMR in the range near 77, it is deuterochloroform. In other words, the solvent that we are using to take this NMR. Zooming back out, again you'll notice that TMS, tetramethylsilane, is showing up in the spectrum. The appropriate reference if you have TMS in the spectrum is of course 0.00. It's defined to be 0 for both carbon and for proton NMR. But if you only decide to reference based on the CDCl3 triplet, then what you should do is set this middle peak here to be 77.16. Once again, if you have TMS, I recommend using TMS as the reference. If you only have chloroform, then set the middle peak to be 77.16. Now what you see is that there's nothing over here on this region of the spectrum, and we don't care about this peak as well, so let me zoom in on the remainder. This is chloroform and can be ignored, so the first level of analysis in a carbon spectrum is how many peaks do we have? Ordinarily, when you click the pincer button here in the carbon spectrum, it actually does a reasonable job of identifying the peaks, far better than on the proton. And what you'll see is that simply clicking on this gave rise to 4 different carbon peaks, ignoring the CDCl3. And so that actually is the first level of analysis of the carbon spectrum. We have 4 carbons. Moving back to the proton NMR spectrum for a second, let me point out that the same level of analysis here on the proton spectrum says that we have 2 hydrogens in this environment, we have 3 hydrogens in this environment, and 3 hydrogens in this environment, which is to say that we have 8 hydrogens altogether. So, in the carbon, we have 4 carbons, and in the hydrogen spectrum, we have 8 hydrogens. That's a good place to start our analysis, and for that, we'll move on to ChemDraw and start to draw some things. So here we're still trying to analyze the EAB spectrum, but now I want to talk a little bit about what we must have learned already. So moving on to ChemDraw, recall that what we learned from the carbon spectrum is that we have 4 carbons. So what I've done now is draw 1, 2, 3, 4 carbons. There is a neat feature in ChemDraw where if you click on the Marquee tool and then go to View Analysis window, it will tell you what the molecular formula of this structure is. And what I think you'll see is that for our 4 carbons, we should have 10 hydrogens present. So what that suggests is that if we have 4 carbons, and we really do have 8 hydrogens, then what must be present somewhere is a double bond. If we have a double bond present, then we have 4 carbons and 8 hydrogens. You'll recognize this as being a degrees of unsaturation type analysis. Now, there are many ways to achieve having a double bond in the structure. We could have the one I drew there. Alternatively, we could draw a double bond elsewhere in the molecule, and as long as this new double bond does not contain a carbon or a hydrogen, then what you'll see when we analyze this structure is that it is C4H8. With an oxygen present, of course, but at least this also, it would be a structure that could be consistent with the number of carbons and number of hydrogens that we have. When you are given the molecular formula, it's easy to start putting the NMR into context. When you are not given the molecular formula, then you have to start playing games like this. For the analysis that we're doing here, all we know is that there are 4 carbon atoms here, 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 and here, ignoring the CDCl3. And we have 8 hydrogens, 2, 3, and 3. Therefore, we must have a double bond in the molecule somewhere, be it like this, or potentially, if we're allowed to have an oxygen in the molecule, then it could be something that looks like this. So now that we've started to think about the framework of the molecule, it's time to analyze the NMR in a bit more depth. I always recommend starting with the carbon NMR because it reveals a fair bit of information and is also relatively easy to interpret. If we're looking at this carbon NMR and we're ignoring the CDCl3 at 77, then what you see is 4 carbon peaks. While things can become more complicated, the first level of analysis surely says that we have 4 carbons as we've been discussing. There's more that we can analyze from the spectrum than simply 4 carbons. Notice these 2 carbons are between 50 and 0 ppm, which suggests that they are at the end of a carbon chain. This carbon here is in the range between 50 and 100 ppm, and generally between 50 and 70, which should give us an indication that it might be next to an oxygen. So we're already thinking that there's an oxygen present in the molecule. Then over here we have a carbon in the range between 150 and 200 ppm, and that should specifically start to make you think that a carbonyl is present. So what I take from this carbon spectrum is that we have two boring carbons at the end of chains. We have a carbon that is next to an oxygen, and we have a carbon that is doubly bound to an oxygen. In other words, maybe the right thing to be thinking about is not only having a carbonyl present like that. Somewhere in the molecule, we must have an oxygen atom bound to a carbon. When you're doing NMR analysis, it is particularly useful to draw structures that are partially solved. And one way to do that is to simply draw pictures that look like this, where what we've started to do is to draw that there must be a carbon bound to an oxygen, and then there is some other bond coming off of that oxygen, which may or may not be defined for us. I have now learned that the video software and ChemDraw don't coexist well, so I'm going to draw some things off the screen and then talk about them once they have been created. Based only on the carbon NMR, then, what we have learned so far is that there is a carbonyl somewhere in the molecule, as judged by the carbon around 171 parts per million, but we don't know what it's attached to, which is why I have put these squiggly lines over the bonds. And by the same token, we know that there is a carbon bound to an oxygen somewhere based on this peak here near 60 parts per million in the carbon. But, once again, we don't know what's attached on either side. A better way to represent the carbon bound to the oxygen is, as you can see here, we know that there must be a carbon bound directly to the oxygen, but we don't know what the oxygen is bound to, and we don't know if there are any other bonds to this carbon. Incidentally, this is the proper way to go about doing NMR analysis. You should immediately start drawing fragments once you've figured out things that must be present. So from the carbon NMR, what we learned was there must be a carbonyl, there must be a carbon immediately bound to an oxygen, and we really have no other information. There are two other carbons in the spectrum somewhere. So now we should go back and consider what the proton NMR is telling us. And what do we see here? We have a tall peak worth 3, a triplet worth 3, and a quartet worth 2. I always recommend starting with the easy peaks when looking at the proton NMR. And in a molecule like this, ordinarily my eye is drawn to the peak that's furthest downfield, because usually that's telling you something about the chemical shift. It's telling you something about what this is bound to. The other thing that's usually easy to look at is peaks that are worth 3 hydrogens, because those are invariably methyl groups. So now that we have looked at the carbon spectrum, and we've decided that we have an oxygen present as a carbonyl, and we have an oxygen present bound directly to a carbon, then perhaps we're in the context to be able to start interpreting this proton spectrum better. What might this peak be? Well, the chemical shift suggests that these are two hydrogens that are bound to a carbon that are bound directly to an oxygen. In other words, what we have there is a fragment that looks like this. We have an oxygen bound to a carbon and two hydrogens bound to that carbon. These hydrogens would have a chemical shift near 4, 3.5 or 4, somewhere in this range, like this. And there are two hydrogens in that environment, so the integral should be 2. And you'll see that clearly that makes sense. However, there are always 3 pieces of information that you should glean from every proton peak. The first is chemical shift. What is this bound to? The second is integration, which is to say how many peaks are in this environment. And the third is how many neighbors are nearby. So if we have a quartet, then that necessarily implies that there are 3 hydrogens near this peak that are giving rise to that splitting pattern. So what that specifically tells us is that near these 2 hydrogens, there must be 3 hydrogens. Over on this side, with the oxygen, there can't be any hydrogens. Therefore, what we have are 3 hydrogens over here. In other words, we have now established that the fragment must correspond to this. We have a peak at 4.2 that is a quartet worth 2 hydrogens. Why is it at 4.2? Because it is two hydrogens bound to a carbon next to an oxygen. The integration is 2 because there are 2 hydrogens in that environment. And that peak is a quartet because there are 3 hydrogens acting as neighbors to this peak. This single peak at 4.1, quartet worth 2, gives us all of that information. It specifically tells us that there is an oxygen present nearby, 2 hydrogens in this environment, and 3 bound nearby that are splitting that into a quartet. It doesn't necessarily imply that an oxygen specifically is present, but it strongly suggests that an oxygen is present. It does, however, say, beyond a shadow of a doubt, that there is a electron withdrawing group out here, a strongly electronegative atom, like an oxygen, like a chlorine, like a fluorine, something like that. So if you choose the right peak to analyze, it's amazing the amount of information you can pick up. Always choose to analyze the easy peaks first, and look how much we've already learned. We have learned where 2 of the 4 carbons must be, and we've learned where 5 of the 8 hydrogens must be. And we've even learned more than that. Notice now that we have defined what is near this peak right here, and so we should contemplate what this peak would look like in the Proton NMR. It is at the end of a chain, therefore it should be near 1 ppm, give or take. However, it is somewhat close to an electron withdrawing group like an oxygen, so it might be shifted slightly to the left. For example, 1.5, 1 to 1.5, or thereabouts by parts per million. There are 3 hydrogens in this group, so it should have an integral of 3. It is a methyl group after all. And furthermore, there are 2 hydrogens nearby serving as neighbors, therefore this should be a triplet. So now we return to the proton spectrum and zoom back out, and do we see peaks near 1 and a little that are a methyl group, or 3 hydrogens, and a triplet? Yes, we do. So now we have successfully identified 2 peaks in the proton spectrum. The quartet near 4 was clearly this peak, and we've now identified the triplet worth 3 near 1.2 as this peak. So we've really learned quite a bit. If we come back to this proton spectrum and we zoom back out, really there's only 1 peak left to analyze, and that's this one. So what can we glean from this peak? Well, it is a singlet. It has no neighbors. It is worth 3, which means that we must have a methyl group, and its chemical shift is around 2. If you look at chemical shift tables, what that will strongly suggest to you is a peak that happens to be corresponding to a methyl group near a carbonyl. So that peak right there specifically suggests that the group that we are looking at is this. You can easily see why we would have 3 protons serving as the integral, because this is a methyl group. There are no neighbors nearby because of the carbonyl, therefore it is a singlet. And the chemical shift makes sense because what we have now is a methyl near a carbonyl, and that usually comes around 2. So we have now identified 2 likely fragments. It's time to take stock. We knew already that we should have 4 carbon atoms, and we should have 8 hydrogen atoms. We weren't sure about the number of oxygens present. We did not have that explicit information. However, we did know that we had 4 carbons and 8 hydrogens. And notice we have 1, 2 carbons, 3, 4. We also have 3, 6, 8 hydrogens. The 2 oxygens are plausible, but they're not guaranteed. And we have 2 fragments, so there's an obvious connection to be made here. As you can see, what we have now is the molecule ethyl acetate. It has the appropriate formula. We have a methyl group with no neighbors near 2. We have a quartet near 4 worth 2. because this here has 3 neighbors. And we also have a methyl group at 1.2 with 2 neighbors, so therefore it is a triplet. You'll find that this structure is indeed consistent with the proton NMR spectrum and the carbon NMR spectra from which we extracted all this information.